Okay, why don't we get going? Okay, good morning. Today we're going to talk about resting potentials and action potentials. Well, it turns out that all the sensory information that comes into the nervous system from the periphery, and similarly all the motor commands that are generated by the nervous system to go to the periphery, are mediated by so-called nerve action potentials. These nerve action potentials are also the first step in the process of excitation-contraction coupling in muscle cells. So in order to understand how the nervous system works, and how muscle cells contract, you need to have a fundamental understanding of action potentials. Now, the existence of so-called animal electricity was known since about 1794 with the work of Luigi Galvani. And what Galvani did was to build a contraption where he could generate electricity. And what he did is charged up this electrode and then positioned the electrode so that one end would touch the exposed spinal cord and the other end would touch a muscle. And what he observed was the following, which at the time was an incredible result. He showed that when the electrodes touched the spinal cord and muscle, there was this dramatic reflex contraction. So based on this observation, Galvani suggested that nerve cells and muscle cells work via electric mechanisms, so-called animal electricity. And he went on to show that this same kind of technique could be used just not on frogs, but also if you place an electrode on a human, you could get a contraction. Now, unfortunately, that theory lay dormant for hundreds of years because there was a big debate about whether the electricity was inside the cells, the nerve cells and the muscle cells, or whether the nerve and muscle cells were simply responding to the nasty shock. It wasn't until the development of modern-day electronic amplifiers and recording devices where it's possible to understand the role of electricity in the nervous system. And some of the questions at the time were, well, how does a nerve cell distinguish between a weak stimulus to the skin and a strong stimulus to the skin, a dim light versus a bright light? How does that electricity in one part of a nerve cell get propagated or transmitted to another part of the nerve cell? And how does that electricity jump across one nerve cell to another nerve cell or one nerve cell to a muscle cell? Well, the experiment done in 1934, was it, I believe, 1934, by this man, H.K. Hartline, provided fundamental insights into the role of electricity in encoding and propagating information in the nervous system. Again, he took advantage of modern amplifiers and recording devices, and he also took advantage of a strange, somewhat unpromising animal that was very amenable to doing these kinds of experiments. Does anybody recognize it? It's a horseshoe crab. If you visited the beaches along the east coast of the United States, you've probably seen this up on the beaches. It's a very ancient animal. It's been called actually a living fossil. It's been around for more than 100 million years. It was around before the dinosaurs. Now, why this was an attractive experimental system is because one could make a small slit in the shell of the animal and expose the optic nerve, and then connect electrodes to the surface of the optic nerve, and then put those electrodes to an amplifier where they could be displayed on a recording device. Then one could present lights of various intensities to the eye. The optic nerve, of course, is carrying the information from the eye to the animal's brain. And what Hartline found was the following. Well, with a dim light, nothing happened. But as the intensity of the light increased,
he found that there was this sequence of these events. Dim light, brighter light,
and
even brighter light.
So what this told him were three very profound aspects of how the nervous system uses electricity to encode and transmit information. First aspect of these spike-like events, and it's these spike-like events that are called action potentials. They're also called impulses. First observation was that action potentials are elicited in essentially an all or nothing fashion. Either you have an action potential or you don't have an action potential, right?
There's no such thing as a half of an action potential.
The other thing of note is that the action potential, although it's difficult to see on the time scale here, this is a 1 second calibration mark, the duration of the action potentials is very, very brief, only about 1 millisecond or so in duration. And the final general principle that emerged from these studies done in 1934, almost 100 years ago, is about the ways in which information is encoded in the nervous system. Note that when the intensity of the stimulus changes, what changes? It's the frequency. It's not the size of the action potential. The action potential doesn't get larger with a larger intensity stimulus. It's the frequency or number of action potentials that encodes the intensity of the information. That's called the principle of frequency coding in the nervous system. It's a very general principle. It applies to all sensory inputs to the central nervous system. And on the motor side, it also applies to the motor system. The greater number of the action potentials in a spinal motor neuron, the greater will be the contraction of a muscle. So what we need to do then, given that these action potentials are so important, we need to understand their ionic mechanisms. How is it possible that they're generated, and how does an action potential propagate from its site of initiation to the central nervous system? And I think, needless to say, just as action potentials are initiated in an all or none fashion, they're also propagated in an all or none fashion. So if you initiate an action potential here, it's propagated unattenuated to the central nervous system. So we need to move beyond the so-called extracellular recordings, where we place electrodes on the surface of the nerve. And incidentally, you're probably familiar with different types of extracellular recordings already in the medical arena. Anybody can give me an example of another type of extracellular recording that neurologists use frequently? EEG, electroencephalograph. EMG, I'll give you a hint, they all start with an E and they end in a G. EKG, right? That's 3. There's also an EOG, electrooculogram, an ERG, electroretinogram. All these kinds of recordings are made by placing electrodes on the surface of a so-called excitable membrane, like a nerve or a muscle. We need to move beyond these extracellular recordings and find out what's actually transpiring across the neuronal membrane. And here is a schematic diagram of how we can do this. We use something called a microelectrode. So here is an idealized nerve cell. You see its cell body and axon, and these are the dendrites, which you're going to hear about a lot more later on. And in the extracellular medium is placed this microelectrode. Now, a microelectrode is nothing more than a thin piece of glass, which is stretched under heat to give a very fine point. The tip can be less than a micron or so in diameter, so the tip can impale the neuron without causing any damage. The electrode is filled with a conducting solution and then connected to a suitable recording device, like this oscilloscope. When the electrode is in the extracellular space, no potential is recorded. But when the electrode then penetrates the membrane so that the tip of the electrode is now inside the cell, there's a sharp deflection on the recording device. Here, about minus 60 millivolts. The potential that you record when you impale a living nerve cell, or any cell for that matter, is called the resting potential. It's a property of all nerve cells, but it's also a property of all cells in the body, resting potentials. And that potential, in the absence of any stimulation, remains constant for indefinite periods of time, unless you remove the electrode from the cell and it returns back to 0 millivolts. The resting potential here is shown as minus 60 millivolts. That's kind of an average value. It's nothing that's absolute. Some neurons have resting potentials of minus 55 millivolts. Some have resting potentials of minus 70 millivolts. But what is common is that all cells have resting potentials, and they are negative inside with respect to the outside. and generally in the range of 50 to 70 millivolts or so. Okay, so that's the recording of the resting potential. What about the action potential? In order to do that, we need to move to a somewhat more complicated situation where we not only record the resting potential with this one electrode, as I showed previously, but in this case, the neuron is also penetrated with a second electrode, which for reasons that will become obvious in a moment, is going to be called the stimulating electrode. So you have the recording electrode just as we showed previously. Now there's another electrode that has impaled the cell. And this electrode is going to be connected to a suitable stimulating source like a battery. Now there's two ways you can connect a battery to any circuit. You can connect the battery such that the polarity as is shown here, and you can also connect it in such a way as shown here. Let's talk about this one first. This is an electronic symbol for a switch. The arrow is up, but if the switch is closed, the arrow goes down, and essentially what that will do is to connect the negative pole of the battery to the stimulating electrode, which in turn is inside the cell. So before I actually run the animation, just think for a moment what might happen to the membrane potential of this neuron. More negative. If you connect the negative pole of the battery to the inside of the cell, you're going to be adding negative charge to the inside of the cell. So in this case, it's going to be made more negative. Now here's a little animation. What's going to happen here, I'm going to press the play button, and by the way, you will have this in your electronic syllabus. And not only going to be opening and closing the switch, but we will be changing the size of the battery, starting with a small battery, right? You can have different size batteries. This could be a 1.5 volt battery. It could be a 6 volt battery. It could be a 9 volt battery. It could be a 12 volt battery. And intuitively, you might think, if we change the size of the battery, how is that going to affect the degree to which the inside of the cell is more negative? Should be proportional, right? Let's see if that's what happens. Small battery, larger battery, larger battery, larger battery. Okay, so here we see that each time we closed and opened the switch, the membrane potential became more negative. Now here's just some terminology that you need to know. Anytime you make the inside of a cell more negative than it was at its resting state, that type of potential is called a hyperpolarization, right? Hyper means more. It has a greater polarization, more negative. Okay, so here what you can clearly see is the degree of the change in potential is proportional to the magnitude of the stimulus that's used to produce it. Now let's flip it around and put the battery in, but now orient the pole, the polarity of the battery, such that the positive pole of the battery is going to be connected to the stimulating electrode. What do you think is going to happen now? More positive, exactly. So let's go through the simulation. Again, we'll start with a small battery and increase the size of the battery. Small battery, somewhat larger, somewhat larger, somewhat larger. And here, of course, is the interesting case, where the battery, we change the potential of the nerve cell. And by the way, the terminology here is anytime you make the inside of the cell more positive, that's called a depolarization in contrast to a hyperpolarization. So you see over a range of stimulus intensities, the magnitude of the depolarization is proportional to the stimulus. And then you reach, though, a certain potential, which, for obvious reasons, is called the threshold, and that leads to the generation of this all or nothing action potential. And what you see here also is the fact that if you make the battery even larger than the battery that was used here, you'll still get the same all or nothing action potential. Now, there's some terminology that you need to know about because the action potential has different phases or components. The first we'd already talked about, that's the threshold. Then there's this portion of the action potential where the membrane rapidly changes from this negative value to the inside of the cell transiently becomes more positive than 0. So this is called the depolarizing phase of the action potential. It reaches its peak in a very brief period of time, and then you have this other phase of the action potential, which is called the repolarizing phase, right? So we have threshold, depolarizing phase, repolarizing phase. There is the peak value. There's a region called the overshoot. That's the region between 0 millivolts and the peak value. And then finally, there's this very interesting aspect of the action potential. When it returns back to the resting potential of minus 60 millivolts, you see that it just doesn't return to minus 60 millivolts. There's a period of time when the action potential, the memory potential, is more negative than the resting potential. And this is called the undershoot. So we have the overshoot, and the complementary part would be the undershoot. And this undershoot is also called the hyperpolarizing after potential. Okay? So we're going to be using this terminology a lot, so you need to, unfortunately, commit this to memory. Now, where is the frequency coding that we talked about previously here? You see the all or nothing nature of the action potential. You see the very brief duration of the action potential, only about 1 or 2 milliseconds in duration. Where is the frequency coding? Here we used a larger stimulus than this one, but we still just got one action potential. Well, it's a little bit of a trick question, because the reason why you don't see the frequency coding is because the stimulus duration here is so short, only a couple of milliseconds, there was only enough time to initiate a single action potential. If you want to see the frequency coding, we can go to the next slide. So here, we're going to see a panel of 4 different animations. Now, instead of a brief 5 millisecond stimulus, I think the stimulus is going to be 20 milliseconds in duration. We're going to show what happens with a small battery, a larger battery, and even a larger battery, which we're going to call a strong stimulus. So here's the weak battery that is actually not even going to do anything except produce a small depolarization. Right? Turn on the battery, we've got a small depolarization, but it was subthreshold. Here is a larger battery. Just one action potential. Obviously, things would go much faster than this if this was real time. This is slow motion, right? Okay, and one more to show the point. So what we're seeing here is a recapitulation of the frequency coding. The number of action potentials is a graded function of the intensity of the stimulus used to produce them. So one question which may come to mind is, why is it important, or is it important at all, to have a duration of the action potential being very brief, 1 millisecond or so? Now remember back a couple of weeks ago you learned about action potentials in cardiac muscle? What's the duration of an action potential in a cardiac muscle cell? 1 millisecond? 20? 40 milliseconds. Everybody agree? 40? Don't know? 40? I don't know. How about 1 second? 1 second? No, don't be so easy. It's not 1 second. It's more than 40. It's more like 100. It varies a lot depending upon, whether you have norepinephrine or acetylcholine, right? But it's long. It's not, the point is, it's not 1 millisecond. It's a lot longer than 1 millisecond. Let's just say it's 100 millisecond. Why do you need 100 millisecond duration action potential in the for the cardiac action potential? Well, you need time for the calcium influx to flow and activate the contractile machinery. Why don't nerve cells have 40 millisecond action potentials or 100 millisecond action potentials? Why 1 millisecond? Well, let me just give you a thought experiment. What if the action potential duration in a nerve cell was 1 second? You couldn't have as many, actually. If the action potential was 1 second in duration, and let's say you had a 1 second duration stimulus, how many different stimulus intensities could you encode? It'd either be on or it'd be off. If you had an action potential duration of 1 millisecond and a stimulus duration of 1 second, how many action potentials could you encode? 1,000. Not only how many action potentials could you encode, but how many intensities could you encode? So having a brief action potential allows this frequency coding principle in the nervous system to work very effectively. So we'll see that the nervous system uses a lot of elaborate mechanisms to make sure action potentials are transient and brief. Okay, now we need to move on to a discussion. Let me just show you this slide first, which is a summary of what we talked about. So here's our little experimental system where we have an idealized nerve cell. We record the membrane potential. We can induce artificial currents into the cell to either hyperpolarize it, make the membrane potential more negative, or depolarize it, make the membrane potential more positive. If that depolarization reaches a critical level, the threshold, we get the all or nothing action potential. We have the depolarizing phase, the repolarizing phase, the undershoot, or the after hyperpolarization. This is what you get with a little brief stimulus, but now if you make the intensity longer in duration, now you just don't have one all or nothing action potential. You have a train of action potentials, the frequency of which is dependent upon the magnitude of the stimulus. Okay, so now we want to try to explain what underlies the threshold, what underlies the depolarizing phase of the action potential. What are the ionic mechanisms accounting for the repolarization of the action potential, and what are the mechanisms underlying the after hyperpolarization? Now, to understand the mechanisms of the action potential, we actually have to take a step backwards and look at the mechanisms of the resting potential, because the two are really intimately related. The story of the resting potential goes back to 1902, when an early physiologist by the name of Julius Bernstein proposed the first satisfactory hypothesis for the resting potential. What Bernstein knew was that there was a high concentration potassium ions inside the cell and a low concentration of potassium outside the cell. And it also appeared as though the membrane was highly permeable to potassium, but not very permeable to any other ion. If you have a high concentration of potassium here, what is potassium going to try to do based on its concentration gradient? It's going to try to move out of the cell, right? Now, Bernstein also knew of the work of the physical chemist, Nernst, and Nernst developed an equation. It said that the potential difference generated across a membrane, which was only permeable to potassium, could be described by this equation called the Nernst equation, which is 60 times the log of the outside potassium concentration divided by the inside concentration. So what Bernstein suggested, was that the membrane potential, and this is the question mark here, the membrane potential was equal to the potassium equilibrium potential. So if real cells were like this artificial membrane that Nernst described, their membrane potential, and if they were permeable only to potassium, then you could predict the resting potential based on a knowledge of the difference between the concentration between the inside and the outside of the cell. So the idea here is that the positively charged potassium would leave the cell, exit the cell, and leave negative charge behind. Now, this equation is called the equilibrium potential for potassium. Why is it called the equilibrium potential? Where is the equilibrium here? Well, there's an equilibrium because there's a balance of forces. One force is the concentration gradient. That's right here. That's the concentration gradient. Potassium is at high concentration here, low concentration here. So potassium is going to tend to diffuse out of the cell. But now ask yourself, what's the consequence of potassium leaving the cell and leaving negative charge behind? Well, that potential that's generated is going to tend to oppose the movement of the potassium outside. So as the potassium leaves, it's going to leave negative charge behind, which is going to tend to pull back the potassium. And when the two forces are equal and opposite, then you have the equilibrium potential for potassium. Now, I like to think of these membrane channels. We're going to hear a lot about membrane channels this week, like little donuts, right? They're little pores in the membrane, and ions can move through those pores, right? There's a whole bunch of these different donuts. Now, this is a big version. Here's a big version of a donut. You know what this is? What kind of ion? So potassium's inside the cell, like me. It wants to go out. Plus on the outside, and there's me negative in the inside holding it back, right? Yeah. We'll talk more about him later. Okay, so that was the hypothesis. Now, how do you test this hypothesis? Now, back in 1902, again, Bernstein didn't have the instrumentation to actually test this hypothesis. If you want to test the hypothesis, what would you do? Well, I want to tell you a very simple way of doing it. This says that the equilibrium potential is equal to the membrane potential. What determines the equilibrium potential? The potassium outside, the potassium inside, right? So I can measure the potassium outside. I can measure the potassium inside. I pull out my calculator. I determine EK, right? And now I take my microelectrode and impale the neuron and ask, is the potential I measure equal to the potential I calculated? It's as simple as that, right? Would that prove it to you? Yes? If they match up, yeah, if they match up. If the potential I measure is exactly equal to what I calculate, you would believe it. I would say that would be necessary. That would be a necessary requirement. But it wouldn't be sufficient. Why? Because maybe the membrane potential has nothing to do with potassium. Maybe there's some other ion, hydrogen ions. The membrane is very permeable to hydrogen ions, and equilibrium potential for the hydrogen ions is minus 60 millivolts. So it just could be a coincidence. So how do you really test it? That is necessary, but how do you test the sufficiency thing? Based on Nernst, if you change the potassium concentration over here systematically, that's going to change the equilibrium potential. That's a given. Nernst is always right. If this changes, is this going to change as well? And so this is the experiment that was done. Here, we're changing the potassium concentration systematically to these different values. Here, it's 100 millimolar. Here, it's 50 millimolar, and so forth. And we measure the membrane potential. This green line is the straight line predicted by the equilibrium potential equation for potassium. 140 is the intracellular concentration, which is fixed. K0 is the extracellular or outside concentration, which is manipulated. And you can see the remarkable result is that the experimentally measured points fit very nicely on what was predicted by the Nernst equilibrium potential for potassium. So does that prove it? No? How many say we're done with this part of the lecture, we can move on? No. It's what? What's your problem? It's accurate, oh, you're saying it's just a narrow range. It's accurate within the range. Yeah, that looks real good. But you want to look down here? You want to look down here. Okay, there's a problem. I admit it. You're right. It does a very good job in this range, but when the concentration gets lower and lower, there's deviations between what you measure and what you expect. And it gets worse and worse as the concentration is decreased. So what does this mean? There is another ion in play. And what is that other ion? Sodium. Now we can talk about sodium. So, how does sodium fit in the picture? Well, sodium is in high concentration outside the cell, and it's in low concentration inside the cell. So if you're sodium outside, what do you want to do? You want to go inside. And what would be the consequences of some of that sodium going inside? It's going to make the membrane potential more positive than you'd expect based on a membrane that was only permeable to potassium. Now we have a membrane that's actually permeable to 2 ions, not 1. Sodium. So sodium's outside, it wants to go in, potassium's inside, it wants to go out, and the two are working against each other, essentially. Now there's a new equation you need to know. You need to know the Nernst equation, but there's a new equation that allows you to actually predict the potential generated across the membrane, which is permeable to 2 ions, in this case sodium and potassium. And that's called the Goldman-Hodgkin-Katz equation. And that equation states that the membrane potential is equal to 60 times the log of the outside potassium concentration divided by the inside potassium concentration. Looks kind of similar. Plus alpha, I'll say what alpha is in a minute, the outside sodium concentration. And the inside sodium concentration. Alpha is the ratio of the sodium permeability to the potassium permeability. Right? Permeability is just a measure of the ease at which an ion can move through a channel. Now this looks complicated at first. By the way, this equation is the Goldman-Hodgkin-Katz equation, after the names of the individuals who developed it. Goldman developed this equation while he was a medical student at Columbia University in the 1950s. Okay, so this looks complicated at first, but let's pare it down to size, right? What if there was no sodium permeability? The membrane was only permeable to potassium. Sodium permeability is 0. That means alpha is equal to 0. So what does the Goldman-Hodgkin-Katz equation reduce to? The Nernst equation for potassium, right? Yeah. What if, let's not make the potassium permeability 0. Let's make it something that is very small. So that means that this alpha value becomes very, very large. If alpha is very large, then you have a large term multiplying this sodium concentration, a large term multiplying this sodium concentration. So these terms become relatively very, very tiny. And what does the Goldman-Hodgkin-Katz equation revert to when the membrane is highly permeable to sodium and not so permeable to potassium? The equilibrium potential for sodium. You can calculate an equilibrium potential for potassium, for sodium, for calcium, for hydrogen. Any ion there is, you can calculate an equilibrium potential for. The Goldman-Hodgkin-Katz equation, if you have a membrane that's permeable to 2 ions, and the limit, if the membrane is only permeable to potassium, you get the equilibrium potential for potassium. And the other extreme, when the membrane is only permeable to sodium, you get the equilibrium potential for sodium. Okay, now we can look at our little plot once again. So here is the same data I showed you previously. These are the data points when we manipulated the extracellular concentration of potassium. This was the straight line predicted by the equilibrium potential for potassium. And here is the line, or curve, if you will, predicted by the Goldman-Hodgkin-Katz equation when the potassium concentration is varied. Now, it's still not perfect. But you can see there's a much better fit over the entire range of the concentration change. So this then shows that you can predict the potential across the membrane that's permeable to sodium and potassium pretty uniquely by knowing, in particular, the ratio of the sodium to potassium permeability at rest. What is that ratio that works? There's a key number here. There's a key number, somebody said it. It's right here, 0.01. So this is the ratio of PNA to PK. What does that mean? That means that Bernstein actually was pretty close to being correct. He said the membrane potential could be predicted by a membrane exclusively permeable to potassium. Well, the membrane is not exclusively permeable to potassium. It's also permeable to sodium, but look at the ratio. It's only 1/100th. So the sodium permeability is there, but it's only 1/100th of the potassium permeability. So for every 100 of these that are going out, just one of these is going in. Okay, so now that we know everything there is to know about the resting potential, we can move on in the next lecture to describing the ionic mechanisms of the action potential. Okay, so we see you in 10 minutes. Thank you.